I will try to talk a little bit about ways to take advantage of unlabeled data, either in testing or in training time, and I will specifically focus on two subjects that are quite popular in vision and learning, few-shot learning and test-time adaptation, and they should be popular. They should be very popular in medical image analysis as well. So this is also pretty much in line with the previous talk, I would say. Just a quick introduction of these two problems, in case you haven't seen them before. In few-shot learning, you basically assume you have large-scale training on some classes that we call base classes. So you have good embedding, and now you have new tasks, basically, where you see, for instance, in classification problem, new classes that you've never seen before, but just with a few labeled examples, and you want to perform well on these new classes, basically. So if you think about medical image analysis, and perhaps a good portion of methods in medical imaging use pre-training, for instance, from ImageNet, then you could think of this as some kind of baseline few-shot method. So or transfer learning, basic transfer learning is some kind of few-shot learning, because you have new tasks or you have new classes in medical data. So perhaps it's good to investigate ways, principled ways, to try to address few-shot learning. And of course, I mean, it's no secret, modern machine learning algorithms fail to recognize from few concepts, unlike humans. So there is a clear gap to fill here. I mean, you don't have to see a million exotic fruit, a million of examples of an exotic fruit to recognize it. You basically need one or two examples, and that's the idea. Why it's interesting? I guess because we could not label everywhere, and even if you look at vision, I'll go to medical imaging very quickly, and you take a very popular data set, especially in tasks that are dense, like semantic segmentation, then it is no secret that they represent very small portion or subdomains of the real world. For instance, just 30 classes in urban scene and cityscape, and the labeling of one image will take 1.5 hours, basically. So if you go with new concepts, and there are perhaps millions in our life, then you would need more labeled data, and we could not label everywhere. So in medical imaging, labels are not just expensive, but also require medical expertise. I don't think I have to spend a lot of time convincing you about this. I like always this example of CAPTCHA with some medical images, and basically you ask people, or you try to crowdsource it and ask people, where is the esophagus? Obviously, you will have problems with this, right? You could not say, you could not do this for medical images. And more so when you're dealing with very dense tasks, where, for example, you do medical image segmentation in 3D plus time. So it will take hours of radiologist time, not of anybody time. So we have a serious issue. And if we look, for example, at the dozens of public data sets in the MICI community during the challenges, we are not anywhere close to the 5K of Cityscape for these specific reasons. So if we could do it, we would have done it by now, basically. So that's another motivation to investigate few-shot learning in medical imaging, specifically tasks like segmentation. And it would probably be safe to say that perhaps medical imaging is more than 50% about segmentation tasks. So, and on top of this, and I think the previous talk mentioned this briefly earlier, so we have domain shifts. So that is shifts in the distributions of data that make things worse. So assume, for example, you trained the model on some MRI data in one hospital, and then you want to deploy it. So of course you have both labels and data, and you want to deploy it on some target domain where you don't have labels. It could be either a different modality, for instance, CT. Even for the same task here, we are not even talking about different classes or new classes or different concepts. you would observe, and probably many of you would have observed this if you worked on this type of problem, significant drops in performances, even within the same modality, coming from different sites or different subject populations, different machines, and so on and so forth. So there is a serious problem because obviously we could not label everything. And this is a very typical example. So a model trained on the left-hand side on an MRI, and then you try to deploy it on CT. Same task here, it's cardiac image segmentation, structures in cardiac image segmentation, and you get pretty much garbage, almost garbage on this example. Whereas the model performed nicely on the source domain where you have labels. So I guess this is a very popular subject, the so-called unsupervised domain adaptation. So what you would do, you would pretty much leverage unlabeled data in some sense. So what you do is basically you imagine that those, okay, just a 2D illustration of the problem. So imagine those blue points are your labeled data from the source domain. You have some kind of domain shift. These are your unlabeled data on the target domain. And basically you train from all. So this is very similar to some supervised learning in its classical definition. And then you might observe much better corrections of your results on this. So this is the so-called unsupervised domain adaptation. Again, it's popular in vision learning, in medical imaging, tons of papers in the recent years as well, for obvious reason about the interest of the problem. Sorry for that. And the last setting, which should, I believe, be of high interest, and it's quite attracting a lot of interest recently in vision and learning. So imagine that you don't even have access to your source data. You just have access to the model, basically, for reasons of privacy. For instance, imagine a model has been trained on one hospital, and that hospital would not like to share the data. And you just have access to the model, and now you want to adapt on new data without having access to the source. So this is the so-called test time adaptation, and I believe this should be of high interest as well. So this comes to the introduction of the problems, and again, I don't think I'll have to spend a lot of time to convince you about the relevance of these problems, and then of course now, how about, and I will try to show you examples of nice and classical methods from vision and learning that actually could be highly competitive among very convoluted recent literature, in fact, to our surprise. So I'll talk about, and of course, when you think about leveraging unlabeled data, you could not expect magic without giving something more to that unlabeled data. So you would have to give unlabeled data some information. So what kind of information? It could be a structure of the data, of the unlabeled data, for instance, and I will give you a very specific example drawn from classical graph regularization method or manifold regularization, also connected to Markov random fields in vision. You could also give knowledge-driven priors. For instance, in medical imaging, we have tons of them. For instance, it could be anatomical constraints. And I will show you very, very briefly quite cool example at the end where we drive test time adaptation with some shape priors. It could be invariance priors, and the very popular contrastive learning is in fact an instantiation of this, where you embed priors about the invariance, for instance, of natural images with respect to transformations, to affine transformations. It could be multimodal prior. It could come from text, for instance, that is associated with radiology images, and so on and so forth. So in a nutshell, it's leveraging unlabeled data with some prior, either during training time or during testing time. So these are the two examples that I will go through very quickly. So let me just point to a few simple concepts in few-shot learning. So we revisited few-shot learning in the recent year. So again, this is actually scary literature, by the way, mostly dominated by very convoluted techniques based on the so-called meta-learning. It's a very dense literature. So and of course, so the type of training define the method itself, and also the type of prediction at this time. So let me introduce very briefly what is meant by induction and transduction, because this will be important next. Okay, so imagine that you have test data. Basically, in the context of few-shot learning, you might have unlabeled data like these points, and these filled points are your labeled data points. Imagine just a binary classification setting. So in transduction, you basically leverage the statistics of unlabeled data. You take account of this. So you make predictions for a batch at the same time, assuming that you have access to that. And in induction, you basically just make a prediction for one sample at the time. So transduction is popular in few-shot learning. If you look at the few-shot learning, including even works from a few years ago, like Mammal, for example, the very popular Mammal, and many other recent work. So I will not go through this, but why transduction is relevant? So first of all, there are tons of practical scenarios that accommodate transduction. Basically, one of them is very standard in medical imaging is segmentation, because in segmentation, it would be perhaps not a wise idea to treat it as a pixel classification where each pixel has individual prediction, because you have all the pixels at the same time. So you might leverage their statistics. For instance, we observed in this recent work last year in CVPR that a good transductive inference is all you need in comparison to very convoluted meta-learning techniques. It will enable you also to take advantage of the statistics of unlabeled data, and it's actually not new. I mean, it's widely used in classical machine learning. And for instance, very famous works by Vatnik in the 90s, late 90s. Methods like label propagation or graph regularization, manifold regularization, even before the deep learning area, are actually transductive inference methods. So let me just talk briefly about this work that we had in 2020 in ICML. We were quite surprised, actually. So the work draw on concepts that are well known in manifold regularization, and even that connect very well in Markov random fields, which used to be very popular in computer visions in the 90s and the years 2000. So here, the setting is very simple. It's almost a clustering subject to some supervision constraints from the labeled data. So imagine that you have your assignment variable of a point to a class C, and then you basically want to find this. This is a latent variable. So you have a feature embedding for each point that come from the base training. And you have the mean of the labeled data points, basically. So if you minimize this term, this is trivial actually to minimize this term. You basically discover a boundary that assign each sample to the closest mean or the closest class, basically. So if you add something called graph Laplacian regularization, that's very simple, which basically encourage nearby samples to have the same assignments. Then you regularize your boundary in this way, like what you see in this illustration here. And to optimize this type of term, if you don't have a lot of unlabeled data, then you could pretty much do it very quickly with first-order methods. Here specifically, we use something called the concave convex procedure, which pretty much linearize the concave part of your function and give you an inference time that is very short and similar pretty much to inductive methods. So to our surprise, at that time, we found that this very simple transductive methods actually beat by margins many transductive methods based on very convoluted technique based on meta learning, for instance, among others in the literature, in the few-shot learning literature. And when you look at it, it's simple structure regularization, in fact, based on quite classical and old concepts. Actually, it's not just our team. So in the recent years, there are many recent baselines which made quite related observations. And basically observing that basic training outperform very convoluted meta-learning methods. So this is an example of where revisiting classical concepts might be really interesting. So here is also a closer look at test time adaptation. Basically, we use the same idea, the same type of regularization. So what we did here is we looked at test time adaptation methods. So of course, we are dealing with domain shifts. So we try to create different type of domain shifts, different type of corruptions. And then we try to observe what happened to state-of-the-art methods when you, across different scenarios, when you use the optimal hyperparameters of a scenario I, and you use them for a scenario G. So what you observe here, for example, for one popular method, which basically optimize entropy with respect to batch non-parameters, you would see that on the diagonal elements, this might be even detrimental, and you have substantial drops, even sometimes catastrophic drops. So it seems dependent on the hyperparameters, which might be a serious limitation in practice. So what we did here is pretty much the same idea. So the first term is pretty much just the transfer learning baseline, if you want. It's just the prediction of the model. And the second term regularized just the output of the network with some kind of Laplacian regularization. So we call it Laplacian adjusted maximum likelihood estimate, LAME, basically. Very simple method that seems to be stable and behave better across different domain shift scenarios. So this is actually an oral at this conference. So I will invite you, if you're interested in test time adaptation. I believe that there are good experimental insights in this work, and you might want to go and check the talk later this week at CVPR. All right, so I think I still have a little bit of time. And this is an example of priors. So this time it's not structural priors, but actually priors that are, in my opinion, very relevant in medical image analysis. And perhaps younger researchers are not aware of a whole literature before the deep learning time where shape is a big deal in the medical imaging community, and people did a lot of effort to manipulate shapes and to embed shapes as priors to make inference, for example, in segmentation algorithm and so on and so forth. So revisiting also these old and nice concepts might be beneficial, in fact. So here's one example in MICAI this year from our team, but it's actually a follow-up on a series of works like constrained CNN, for instance, where essentially we try to embed priors on the predictions of a neural network. That is basically the softmax output or the probability output of a neural network. So what we did here in test time adaptation, so we have a standard entropy term for test time adaptation, and on top of that, we added a prior that basically encourages just plausible shapes to appear in the solution. So what we did here, we used something called shape moments, which is also very classical in computer vision. There are literally books about this. And we expressed shape moments as functions of the softmax prediction of a deep network. So S theta PC here is the softmax prediction for a pixel P and class C. These are just the coordinates, the image coordinates. And essentially we constrain these shape moments to be within a certain range to encourage only plausible shapes. So you could see here basically the baseline, the transfer learning baseline, no adaptation, and with shape constraints. Of course, I won't be able to go into the details and also to describe the results given the time constraints, but I will give the references later, and I could even share the slides, and feel free to drop an email if you are interested in more details. But this is basically it, and we observe that it's quite competitive, in fact, in comparison to many convoluted methods. So this is it for the methods I wanted to point to, and just time to acknowledge some people. These are not my work, obviously. I'm just talking about them. So these are the works of former and current PhD students. Ziku was looking at Laplacian regularization for few-shot learning 2 years ago in this ICML paper. Shape moments also are, and shape constraints in general in CNN and constrained CNN in general are the works from Howell Kervadex and Mathilde Bateson. And also the test time adaptation works and related few-shot segmentation works are the works of Malik Boudieff, and of course many colleagues also involved in these works. So the take-home message, basically what I wanted to say here is, well, I think these subjects are very interesting, especially now that we are going with the more complex foundation models based on billions of parameters. So we will need adaptation all the time, because not everybody, not every team, not every small company would be able to retrain these models. So adaptation, whether to tackle new tasks or to tackle shifts in the data, will be, in my opinion, the subjects of interest in the coming years. The second take-home message is, okay, read the literature sometimes before 2015, especially to young researchers. So here we found that old concepts are quite useful, like, for example, graph regularization in the context of few-shot learning. So you might end up with a method that is highly competitive among the jungle of very convoluted methods, like in the case of few-shot learning here, and end up with a publication at NeurIPS or MICAI or CVPR. So do not hesitate to read papers and read textbooks from that are old in the literature. I think that's it. Just to comment also specifically for few-shot learning. So I found that this is a very specific case of where a very convoluted literature end up basically not used. So the few-shot community is kind of right now being disillusioned about how the prospect of meta-learning and how it could help. And in my humble opinion, it's we could not expect magic from torturing gradients and batches. So priors are the key. I mean, you have to give unlabeled data some priors to expect really good generalization, basically. So that's it, and I'm happy to take questions. And of course, if you have questions offline, feel free to drop a line, and also we strive to have codes public for all the work, so do not hesitate to use them if you're interested. That's it.